some of these videos. Anyway, what he showed you is that once the way turbulence develops is it starts off, remember, it starts off tumbling, basically rolling down like that. And then it develops a three-dimensionality to it. It tumbles down and over to the side, and then it picks up and comes back again. So it's sort of making helixes. Down, slowing down, out, and then up. And so if you're sitting on the bottom, you'll have streams coming down, or turbulence, high, remember it's very low velocity on the bottom. So you have high velocity stuff coming down right above you and making a streak, we call it, or a burst, where it comes along the bottom and then sweeps up and out and takes sediment with it and squirts sediment out. And I believe I've got a video of that that is a good one. Let's see. I think it's, let's see. Ooh, that's kind of cool. Let's see. Where my street? Oh, there we go. I don't know. We'll see if this works. I think this is, yep, this is it. They have this great model. Okay, there are streaks. Okay, here, this is a numerical model, and the lighter colors represent high velocity. And what you can see is what they do is they come in and sweep material up into the flow. So you get these things of water coming up off the bottom, and then they get caught in the turbulence and destroyed, and then they come down and make another sweep, another streak on the bottom. So it's not just two-dimensional rolling like this. It's three-dimensional. You can sort of imagine the turbulence doing the breaststroke. All right? We'll do a couple, and then this one's kind of a cool one. Anyway, and you can see, and then they make these like hoops that come up off the bottom. It's pretty cool. I think it's this one. Does the, yeah. Okay, forget that. That's the mathematical model. Forget the mathematical model. We want the pretty, there we go. Anyway, here you can see the streaks coming up off the bottom. And now just imagine that sort of being a 3D effect where it's coming up and then eventually sort of growing up into a big hoop and then dissipating in the regular flow. So red here is fast, blue is slow, and yellow is in between. And so, and here is the boundary layer. Okay. Whew. Wanted to get through it. Does everybody get a feel for how boundary layers work? So all this digression that we spent most of today on is just sort of understanding how air and water interact with sediment on the Earth's surface. You don't need to know the math of this. What I do want you to know is that this gradient generates shear stress. It slows the fluid down and tugs on the bottom and tugs sediment up into the fluid. And that you can estimate the severity of the turbulence by the Reynolds number. The higher the Reynolds number, the more turbulent the flow is. And therefore, the greater the shear stress. Okay. And so, one of the things we will do in our problem sets are calculate the, let's see, there's a picture I took that does a 3D modeling. Let's see, what else? Okay, we did boundary layers, fluid, shear stress. Okay, do we have time for settling? We got 5 minutes. Okay, before I move on, any questions? This is where I wanted to get to today. Okay, the last thing, so far we've just been dealing with fluids. Now we're going to add sediment grains. And we're going to add them in the most simple way possible. We're in a lake, wind blows some sand and dust into the lake, it settles down through the fluid. How fast do particles settle in a stagnant fluid? And there's a equation that covers that, and this is it.
Oh,
and
Stokes.
It's the V for velocity of the particle. Remember, we use U for fluids. So V is actually the velocity of the moving particle. Is equal to 1/18 times the density of sediment minus the density of the water. We call that the buoyant density. So, you know, if you're trying to pick up and carry a person in the air, they're really heavy. And if you're in a swimming pool and neck deep in a swimming pool, you can pick them up pretty easy because the water is pushing up also and making that person weigh less. Or if you're floating in the swimming pool, you weigh a lot less than you do on the ground. And that's your buoyant density. So that's basically the density of the particle is times gravity is the force moving that particle down. Okay, this D is actually, it's
Density of the particle.
is D squared, that's the diameter of the particle squared in meters. And this is the viscosity of water. Okay, this equation is fairly simple. You will probably have trouble with it at first because this gives you some really small numbers. So let's start with, and finish class with, I want you guys to calculate a standard quartz grain, density 2,700 kilograms per meter, and water 1,000, and let's have our grain be, let's make it 4 feet, right at the finest grain sand. What is the settling velocity of something that's the very finest grain sand? What is that so first, what is a 4 feet sand grain in size?
Silt?
What's 0 feet? 1 millimeter. What's 1 feet? Half a millimeter. 2 feet? Quarter. 3 feet?
125.
8. 4 feet, 1/16 of a millimeter, right? So what's 1 divided by 16 is
5.
0.0625. Okay, so it's 0.0625 millimeters. How many meters is that?
0.00.
0.000625.
Yeah. So, or 6.25 times 10 to the minus 5th meters. Either way, if you want to do it. But that's your size, and this is what'll throw you off, is if you don't convert everything to meters, then the numbers come out wrong. So somebody real quick calculate. So what's rho S minus rho W going to be? 1,700, right? So 1,700 times 9.8 times that horrible number. Yeah, squared.
Okay, so that.
So you've got to start with the tiny number squared times 9.8 times 1,700 divided by 1.06. 1.06 times 10 to the minus 3rd divided by 18.
About 4 times 10 to the negative 6.
Okay. Does that sound right? Who's got the power? Up
What's
right.
the viscosity?
1.06 times 10 to the minus third.
Mm-hmm.
Okay, so you got
4 times 10 to
4 times 10 to
the negative 6.
the minus 6. Okay, so we're going to pretend that's, I'm going to assume that's the right answer because I can't calculate it. 4 times 10 to the minus 6 meters per second. So how many millimeters per second is that?
4 times 10 to the negative 9.
So 0.004, right? 10 to the minus third millimeters per second. So how is, and
Are you right? Millimeters. Wouldn't that make the number bigger?
No, to the minus 30.
huh?
To the minus 30.
I'm sorry?
That would be to the minus 30.
Yeah, 4 times 10 to the minus 3. Yeah. So 0.004 millimeters per second. And so it would take 1,000 seconds. Let's see, I'm thinking we might be wrong here. We may have screwed up our calculations. And this is why when it's this big, things get mucked up.
I've got 3.14 times 10 to the negative 3 for the original.
For the original, that's better.
Sorry, I'm doing it on my phone.
Yeah,
today,
because
so-
that's way too slow. So you got, that's better. So you got 3 times 10 to the minus 3?
3.14.
3.4.
Okay, 3.4 times 10 to the minus 3 meters per second. So that gives you 3.4 millimeters a second. Much better. Half a centimeter a second. So if we're in a stream that's a meter deep, it takes, it's drawing 3 millimeters a second. It takes 30 seconds, right? 3 times, yeah, say about 30 seconds to go drop a meter. 3.4 millimeters a second. In 10 seconds, it's gone 3.4 centimeters. No, it's 3 minutes. In 30 seconds, it's gone 34 centimeters. And in 90 seconds, it's gone a meter. So about a minute and a half to drop for the finest sand to fall through a meter of water. So it doesn't take a whole lot of turbulence to keep the finest sand up in suspension in the water. And what I'd like you guys to do, this is in your check out for a coarse sand. Try a 0 phi sand. And try the fine, just go, don't worry about the 10 feet, try 8 feet, try the very finest silt. This is why we divide silt from clay and clay from sand, is this behavior here. Sand and silt and clay behave totally differently, and a lot of it's related to how fast they settle. And I know I'm late, but we're done.